Okay, the 2-methyl radical. This is in case of the last slide. Sure. For the last slide, we have the propagation step and initiation step. So we have our initiation step and we have our propagation step. These two steps or continuous chain. And then we have our three termination steps, like 3 possible reactions that would end up with no free radical that basically stops the reaction. So what everything we talked about is just talking about the mechanism of the reaction, how the reaction is started, how it's finished, what are the steps in between. What else we want to know about a chemical reaction? So basically, when we are studying one single chemical reaction, we want to know the mechanism. We want to know the reaction, if the reaction is so in general, we want to talk about mechanism, thermodynamic for the reaction, and kinetic for this reaction. So thermodynamic for the reaction is going to be, is this reaction endothermic or the reaction is exothermic? Kinetic for the reaction is like how fast this reaction is going to take place and how temperature is going to affect, or what are the factors that is going to affect this the rate of the reaction. So the thermodynamic for this reaction, or any type of reaction. So we're going to study chlorination and bromination in this chapter, just to learn about how we are going to study a chemical reaction. Because for other chapters, then we have different type of reaction. So different mechanism, thermodynamic and kinetic might be different, but the idea of studying a chemical reaction, meaning that we want to know mechanism for the reaction, what is our reactant, what are our product, what type of catalyst is needed for this reaction. Then we want to learn about the thermodynamic. What are the values that are most of our concern when we study thermodynamic of reaction? When we study thermodynamic of reaction, we want to know about delta H for the reaction. What is delta H? Delta H is the energy of the reaction, or the energy change for the reaction. A positive value for delta H, it means this reaction is endothermic reaction. A negative value for a delta H, meaning that this reaction is a exothermic reaction. Heat has been released or heat has been absorbed. For endothermic reaction, heat has been absorbed. For exothermic reaction, heat has been released. So that's one of the thermodynamic value that we are concerned about, the amount of the heat that is being involved in chemical reaction. The other thermodynamic value that we want to know about a chemical reaction, to have a general idea, is the value for delta G. Value for delta G, you have learned about how to calculate delta H, delta G in general chemistry, but we're just trying to study a chemical reaction and have an idea, is this going to release heat? Is this going to absorb heat? And how do we use the value for delta G? If value for delta G is 0, it means the reaction is at equilibrium. So you have an equilibrium where delta G equals 0. If delta G value for a chemical reaction is greater than 0, so it's a positive value, this means that reaction is non-spontaneous. If the value for delta G is negative, that means your reaction is spontaneous. So values for delta H is going to tell us if the reaction is endothermic or exothermic. Values for delta G is going to tell us if the reaction is going to be spontaneous or is not going to be spontaneous. The values for delta G can be calculated using the K equilibrium for the reaction and the temperature, or you can use the values of delta H and delta S to calculate the values for delta G. So now, what is the value for delta S, or what does delta S represents? Delta S is the entropy for reaction, degree of disorder for the reaction. So if the delta S value is positive, that means the entropy has increased. Delta S negative means that entropy has decreased. Which one is favored? Is that increase in entropy is favored for the chemical reaction in order for that reaction to be spontaneous. So these are some of the values that we are concerned about. Values for delta G, which shows the reaction is being spontaneous or non-spontaneous, and to calculate the delta G using delta H. So delta G equals delta H minus T delta S. So we want negative value for delta G, that means a spontaneous reaction, and negative value for delta H, that means exothermic reaction. A positive value for delta S means that entropy has been increased. So to calculate this, most of the concern now is not how to calculate delta S or delta H, is to understand the meaning for values for delta H and delta S and delta G for this chapter. So how do you calculate the value for delta G? In order to calculate the value for delta G, you could have like the K equilibrium, and then you use the formula of delta G minus 2.3 RT and log of the K equilibrium. Or you could calculate the delta G based on the delta H minus T delta S. Either one of them, would work. So we're going to talk about delta H for the reaction. When delta H is calculated, that means heat has been released or heat has been absorbed. What is heat necessary? Why heat is necessary for a reaction? Or when heat is consumed, or when this heat is being released? There is when forms, there are a couple of things that you need to know by heart, like just know it becomes natural. When you have bond forming, energy is being released, and you can memorize that, or you can relate that to formation of the bond and understand why bond is forming to begin with. Let's say you have a chlorine with one single electron, which is very unstable, another chlorine with one single electron that is very unstable. When these two form bonds, is going to make it more stable. Okay, so you get the chlorine-chlorine bond. When you get the molecule of chlorine, chlorine is going to be stable. What does it mean, stable? Stability means that it's going to have lower internal energy. So if it has lower internal energy, looks like the internet is poor, and the video goes pause on its own. So I don't know if it's necessary or not, but so the difference in energy between two atomic chlorine and molecule of chlorine, that is the amount of the energy that is being released when bond forms. So we have bond formation energy. So anytime a bond forms from two atoms, the two atoms, the only reason they are forming bond because they are not stable. They want to be stable, and if they are they become stable, they are going to have lower internal energy. And the difference in the energy level between the atomic chlorine and molecular molecule of chlorine, this amount of energy is going to be released to environment. So from now on, whenever you're talking about bond formation energy, so that is a BFE, bond formation energy is going to be a negative value because energy has been released. And by convention, they say that delta H value, whenever energy is released, is going to be negative. So we have bond formation energy. Now, let's say we try to break this bond between chlorine and another chlorine. By definition, if you break this bond in a way that it goes back to what it was before, if it goes back to what it was before, the two atomic chlorine, 1 electron for each one, that means hemolytic cleavage between the two chlorine. Hemolytic, like same, using the word prefix hemo, it applies to this because when you break a bond that has 2 electrons, one goes to one chlorine and the other electron goes to the other chlorine. So this is for hemolytic. If you have hemolytic cleavage, it's going to take the molecule of the chlorine to 2 atoms of chlorine. So what happens in this case? Is energy consumed or energy is released? When you are, energy is going to be consumed. And how much would be that energy? That energy is going to be, numerical value is going to be exactly the same amount that you have received when you had bond formation energy, because it's taking the molecule to 2 atoms. So we have bond dissociation energy, that is the BDE. That's bond dissociation energy. We have bond formation energy. Bond formation energy is going to have a negative value for delta H because energy has been released. Bond dissociation is the energy required for the bond to break, to go to the atomic level, because going from more stable to less stable is going to be a positive value for delta H because it's endothermic, or the energy has been consumed. So we get a positive value for bond dissociation energy. What is chemical reaction? A definition for chemical reaction is that you learned about physical change, chemical change, or chemical reaction before, but what we are using here is like that is an irreversible process versus physical change that is reversible. In a chemical reaction, old bonds are broken, new bonds are formed. So when there is chemical bond breaking and new bond is forming, you are going to have a chemical reaction. And when you have a chemical reaction, energy is involved. Energy is involved because you have to spend energy to break a bond, and then you will get energy when the new bonds are forming. Now, how a process could be endothermic or exothermic overall? If the amount of energy being consumed is less than the amount of energy being released, overall, your reaction is going to release energy. Now, if the amount of energy being consumed is greater, what does it mean? It means the bonds that you are trying to break, they are a stronger bond. If you have a strong bond you're trying to break, you have to spend more energy. So if the amount of energy you are using or is consumed is greater than the amount of energy being released when the bond forms, then your reaction is going to be endothermic. When you have endothermic reaction, that means the bonds that needs to be broken, they spend more energy or they consume more energy than the energy that you are recovering when the reaction is complete or when the bonds are formed. So you will have endothermic reaction. Where the reaction is getting its energy from, if it's endothermic. If the bonds cannot provide the energy for the reaction, or formation of the bond is not going to pay back and provide the energy for the reaction, the rest of the energy is going to come from environment. So the reaction is going to consume or take energy from the environment, and when they take energy, when the reaction takes energy from environment, the temperature is going to drop. There would be a change in temperature also for the environment. So it's going to absorb energy from environment because you want that reaction to happen. So that would be like for endothermic reactions. So basically, we have to heat up the reaction. If the reaction is endothermic, we have to provide the difference in the energy that is coming from bond formation and what is needed to break the bond. Okay. This overall reaction of chlorination, this is just one step chlorination. So the old bonds that are breaking, you have Cl bond needs to break, CH bond needs to break. Then we have the positive charge for the bond dissociation energy. These two values showing the amount of energy needs to be consumed for this reaction because we have to break this bond. We have to break the CL bond. These bonds are broken. We consume this amount of energy. New bonds are formed. So we have this one is forming. So we have bond formation energy, BFE, bond formation energy. And here also we have bond formation energy. And bond formation energy is negative value because the new bond is forming. It makes the species more stable, meaning less energy. As a result, you are going to get better stability. The excess amount of energy would be released. By convention, energy that is released has a negative value. So if this is the total amount of energy being released, this is the total amount of energy being consumed. Overall, reaction is going to be exothermic. Why exothermic? Let's say if you make $1,500, you only spend $1,000, you end up with $500. So you make more, you make a profit. Like if you are doing a job that is you have to spend $1,000 and then you are getting back $1,500. That's the same idea. So this is an exothermic and heat is being released. For exothermic reaction, you have the energy diagram for exothermic reaction. It looks like this. You start with your reactant. You are going to get the transition state and the final product. So you have your products here. You have your reactants here. That's the amount of energy that your reactants and products have. And transition state is right here. So the difference between energy of the reactant and transition state has one value that is called activation energy, EA value. Activation energy is the energy, the difference between the energy of the reactant and energy at transition state. Energy of the product, the difference between energy of the product and energy of the reactant, this value here is going to be delta H. This is for exothermic reaction. How is that different from endothermic reaction? For endothermic reaction, you are going to have similar, and you are going to have higher value for energy of the product, less value for energy of the reactant. You have your transition state still is the highest energy level when you have the energy diagram. Activation energy and the difference in energy of the reactant and product is going to be delta H. So by definition, you have activation energy for exo, you have activation energy for endo. You have delta H for exo and delta H value for endo. You need to know the definition for if the energy diagram is given, you should be able to label the red marks from this graph, from each of the graph. The red marks that what is the transition state, what is the activation energy, what is delta H, and the difference between endothermic, exothermic reaction. For exothermic reaction, products have less energy than the reactant. For endothermic reaction products, they have higher energy compared to the reactant. The transition state for endothermic reaction is closer to the product. Transition state for exothermic reaction is closer to the reactant. So this is not a very challenging chapter, but these are the highest point of the energy. So it's not, it really doesn't reach the plateau, but it's the highest point of the energy diagram, the highest energy level. Why transition state? Because what's happening at that point, your molecule is in the process of going from reactant to the product. Is not the reactant, is not the product. It's not very stable, and stability is opposite to the energy or internal energy. So it's like if you are moving, you just bought a house, like in this house, like a lot of things happening. The people who were living there, they are leaving, and then you are moving in. One bond is leaving the central atom, one bond is forming, and the central atom is not satisfied with the octet, either has too many electrons or has too little electron. If the bond breaks, you have less than 8 electrons. If the new bond is forming before the old bond breaks, you have 10 electrons for that carbon or the central atom. So it's kind of shaky, and it has the highest energy level. That is called the transition state. Is being transited from the reactant to the product. Okay. So for thermodynamic, we want to know what is the activation energy, what is the energy given energy diagram, what's the difference between endothermic, exothermic reaction, what's the value for delta H, is it positive or negative. Now for the rate reaction, rate could be like first order, second order, and then we have the overall order for the reaction. So this value for the general rate formula is the K concentration of first reactant to the power of A, concentration of second reactant to the power of B. So this power that we have here, that is the order of the reaction. That represents the order of the reaction. So if this value is 1, that means if you double the concentration of A, the value for rate is going to be doubled. So it's like 1-to-1 ratio. If this value is 0, what does it mean? It means that if you increase concentration of A, is not going to change rate of the reaction, because any number to the power of 0 is going to equal to 1. So the rate is constant. It doesn't matter, it's independent from concentration of A, and if you increase the concentration for A, rate is not going to change. If it's second order, that means if A equals 2, that means if you double the concentration of A, the rate is going to be quadrupled. So those are the meanings. Again, just a quick review. We may not use it too often at this point, but we are going to use it in chapter 7, or when we are talking about SN1, SN2 reactions. But just the idea of when we are studying a chemical reactions, we study mechanism for reaction, and I'm just repeating, and we are studying thermodynamic for reaction. We want to know if the reaction is spontaneous or non-spontaneous. We want to know if the reaction is exothermic or endothermic, and we want to study kinetic for the reaction, see if this reaction is fast or slow. Kinetic for the reaction, how fast the reaction is going to take place, it depends on activation energy. So from the energy diagram, you can predict if this reaction is slow or if the reaction is fast reaction. So if you have that reaction A and you compare that to reaction B, what do you need to compare in order to find if this reaction is slow or fast reaction? Is the activation energy. For reaction with higher value for activation energy is going to be a slower reaction. If it's a slow reaction, you would get less product because it has very high activation energy. Activation energy is the minimum amount of energy required for reactants to go to product. Activation energy is a standard, so you do have that energy diagram, and if the activation energy is high, obviously for a slow reaction you would get less product. Like to pass exam, let's say you're taking a PCAT, like to pass that is 70%. If the 70% is the passing rate, not the passing rate, is the requirement, 70% is the passing point, then you might have more students passing than if they say, if you, in order to pass this test, you might get minimum score of 85%. So then activation energy must be higher. Since the activation energy is higher, then the passing rate is going to drop. You would get less students passing or less test takers passing that test going to the product, which is like, I passed the test already. How can you increase the passing rate? In order to increase the passing rate, you expect the people who are giving you the test to bring that test, make it easier, so you get this. And the people who are giving you tests, they expect you to come up here. They say, just if you increase your energy, that means your prep time, you increase your energy, you jump up this much, and then you calculate the new EA value for yourself, and you are getting to, you're to pass that test easier because your energy now is higher. So if the chemicals, they have higher energy, they can go past that activation energy, go to the product. If they don't have, two things should happen. One, you increase the energy of reactant. How can you increase the energy of reactant? You can't change the nature of that compound, but you can heat up, you can increase the temperature. When you increase the temperature, your reactant, even though they have this much of internal energy, now they're acting at the high temperature, they're acting like they are right here at this point. So they can jump this hill much easier. The other way to lower the activation energy is to use catalyst. When you use catalyst, you don't change the energy of the reactant, you don't change the energy of the product, but you are going to change the mechanism of the reaction and make the reaction going through new route, and you get like EA with the catalyst. So with the catalyst, you have you lower the activation energy, and then you would increase the rate of the reaction. When you say I increase the rate of the reaction, what are the benefits? You are going to make the reaction take place faster. That means you get more product for that reaction. Two ways: increase the heat or use catalyst to lower the activation energy. So activation energy is going to affect the kinetic and the rate of the equation. This diagram also shows the activation energy for the reactant. At higher temperature, you get more chemicals that they can have minimum amount of energy, and they can go past the transition state. They can change to the product. So rate of the reaction is related to activation energy, because temperature is one factor which you can control. I said you increase the temperature, you are going to increase the rate for the reaction. But if you use catalyst, you could also change the rate for the reaction. You get more of the products. So this diagram down here, it shows the number of particles, or the percent of the reactants that can actually go to the product side is going to be much higher than this blue shaded area. At a higher temperature, you have that green area, and for the lower temperature you would have blue. So we talked about transition state. You had a question about transition state. Transition state is when the old bond is breaking, new bond is forming, your molecule is going through a lot of stress, and it's represented by the transition state, and you draw it like this, like a plus sign with the 2, with additional dash. So value for delta H, this drawing is kind of more neat. You have delta H, the difference between energy of the reactant and product, and activation energy, reactant and transition state. So if a graph is given with just lines, you should be able to add those writings to it. If the reaction that is taking place, it has intermediate. So basically you have your reactant, you have your product, you also have an intermediate. So if your reaction has intermediate, then you are going to have your energy diagram for that reaction is going to change. This means you have 2 activation energy, and the rate of the reaction depends on the slow step of the reaction. Which is slow? If I call this EA1 and this one EA2, the slowest step of the reaction is going to be the step of the reaction with the higher activation energy. So a slow step of the reaction is going to determine how much product is going to form. So let's say you have two tests. You have board 1 and board 2 tests to take. If your board 1 is the hardest and the board 2 is easiest, and anybody who passed the board 1 is going to pass board 2, but they cannot just take it. They still have to get ready for it. So the EA2 value is not going to be 0, because then you have 1-step reaction. But if you pass the board 1, that is hard exam, there is a much greater chance for you to pass the 2nd step or board 2 exam. So the more stable intermediate, faster reaction. Please keep this in mind, because it's going to help you a lot with the mechanism of reaction in organic chemistry. Because in inorganic chemistry, you don't study basically intermediates. For intermediates that is forming, like free radical was one of the reactive intermediate that was forming. The more stable the free radical, the faster that reaction. And what is intermediate is the species that it forms and it's consumed right away. You cannot isolate free radical in a chemical reaction. It forms and then it is consumed. Okay, what this table is showing you, it compares the reactions of different halogens or halide in halogenation reaction of alkane So if we take the simple molecule of alkane, which is methane, and we make it react with fluorine, chlorine, and iodine, the activation energy, the value for activation energy, the value for rate at low temperature, value for rate at high temperature is given to you. So there are couple comparison here for any of these elements, for any of these reactants, for chlorine, bromine, and iodine. At higher temperature, the rate is higher. And we talked about that before. You increase the temperature, the rate is going to be higher. But based on the nature of the compound, fluorine is the most reactive. So we see that the rate of the reaction is decreasing, going from fluorine to iodine, as increasing going from iodine to fluorine. So fluorine is going to react very aggressively or explosively. Chlorine reacts at moderate rate. So we have a good rate for the chlorine. What does this mean? Is less than 1. The rate of the reaction for bromine is less than 1. This means this reaction is not a spontaneous reaction. This reaction is not exothermic reaction. So if the rate of the reaction is less than 1, that means the reaction is most likely endothermic reaction, and activation energy is high, and you have to heat up or apply heat for this reaction to take place. For iodine, this value is very low, and how we can interpret that, if the value is very low, iodine value for rate is very low for iodine, don't try to change iodine with hydrogen from the methane, because the rate of the reaction is too slow that you don't want to spend that energy or the heat to make this reaction, to force this reaction to happen. So that's how we interpret that table. Activation energy is higher for iodine. The rate of the reaction is lowest for iodine. Activation energy is highest for that. So we're not going to deal with fluorine because the reaction is very fast, and we are not going to deal with iodine. We are going to compare reactions of chlorination with bromination, because both of them, it's doable. One is moderately done and is exothermic, and the other one, with some heat, it can actually happen. For chlorination, what do you see from chlorination? Is this reaction exothermic, endothermic? This reaction, so radicals, I'm sorry, let me read your question one more time. So radicals only deal with halides. Yes, radicals, it's not the only reaction, but at this point, we are dealing with the free radical chain reaction or halogenation of alkane. The mechanism for this reaction is free radical chain reaction, and the intermediate that is forming is free radical. So for this type of reaction, we are dealing with the intermediate of free radical. So mechanism of the reaction suggests that we have formation of free radical for chlorination. So this is step of the reaction. This is basically first step of the reaction. When the free radical is forming, the intermediate is forming, is the endothermic reaction. It's continuous with the second step of the reaction. In the second step of the reaction, you might get actually overall reaction of exo. Depends on the second step of the reaction. But it's comparing that if you get methane changing to the free radical of methyl free radical, this step of the reaction is endo. The more stable the free radical is, the faster that reaction is going to be. So the more stable, that means instead of having chlorine free radical in that level, let's say you have a T-butyl free radical that comes here. So for T-butyl free radical instead of chlorine methyl free radical. So if the free radical is more stable, then this delta H value needed is going to be less, and this is going to form faster. So the more stable free radical is going to form faster. And if you compare that, if you take it to the energy diagram, you see that the delta H value, if it's positive, is going to be less, or if it's negative, is going to be favoring the reaction because it's going to be exothermic. The chlorination for propane. In chlorination for propane, when you add chlorine, now chlorine is going to replace one hydrogen from propane, monochlorination. You have choice of two carbons or two hydrogens. You have a primary hydrogen and a secondary hydrogen. What is a primary hydrogen? A primary hydrogen is the hydrogen that is attached to primary carbon. What is secondary hydrogen is the hydrogen that is attached to secondary hydrogen. So this hydrogen is a secondary hydrogen because this carbon is a secondary carbon. And when we talked about sec-butyl, we talked about secondary carbon. What is the secondary carbon? A secondary carbon is a carbon that is attached to two other carbons. Primary carbon is a carbon that is attached to only one other carbon, so basically this bond here. So that's for primary carbon. Now, if the primary carbon takes the chlorine or primary hydrogen replaced by chlorine, you get only 40%. When the secondary hydrogen is being chlorinated, or the secondary carbon being chlorinated, or secondary hydrogen is being replaced with chlorine, you get 60%. So 60% of the product is going to be secondary product, and 40% is going to be primary. Now, we are dealing with minor product and major product. Yields to major product. The reaction that is faster would yield to major product. The reaction that is slower would yield to minor product. And please remember these, write notes. I know it's in the slides, but make sure you write it in your own word, because if you know all of these facts, then putting it together is going to help you to study the mechanism for reaction and predict what is major, what's minor product. Which type of reaction is going to be faster based on stability of intermediate? What type of product would be faster based on okay, which one is going to be major? Faster the major. But there is another fact, another word that I'm looking for here. What type of, which reaction is going to be faster that would yield to major reaction in terms of stability of intermediate? So you have to use the stability of the intermediate. You have to defend your case based on the stability of the intermediate. It should be in your notes, because we talked about more stable, faster the rate. Very good. The more stable intermediate, and please make sure to say that intermediate, the more stable intermediate, the faster the reaction. Okay, more stable intermediate, the faster the reaction. The faster the reaction, the faster the reaction yields major product. Okay, let's just repeat and apply to this reaction what you just said. And I hope that everyone at this point agrees with what we are saying and is clear. And if not, please let me know. So we have two possible products here. If primary is being replaced, you get your minor product. If secondary is being replaced, you get your major product. What does that mean? Is primary free radical more stable or secondary free radical more stable? Major product is more stable, so is going to be the secondary free radical that is more stable. So if I have a primary free radical, that means the carbon that has single electron is a primary carbon. So this is a primary free radical. If I have the carbon that is secondary with single electron, this is a secondary free radical. So this is a secondary free radical. This is a primary free radical. Secondary free radical is going to be more stable than primary free radical. How do we know that? The result of this experiment, it does prove it, because we already know the fact that the more stable intermediate is going to yield major product. And since this one, a secondary replacement, is our major product, then is going to prove that secondary free radical is more stable than the primary free radical. And also count how many secondary hydrogens you have here. How many secondary hydrogens? You only have 6 secondary, you only have, I mixed the two together. You only have 2 secondary hydrogens, but you have 6 primary hydrogens, right? 2 secondary only, because only these hydrogens are secondary. Only these hydrogens are secondary. These hydrogens are primary, the CH3, and these hydrogens are primary. We have six primary hydrogens. We have 6 primary hydrogen. Is the CH2 for propane? We have CH2. So we have 1 primary carbon, but 2 primary. We have 1 secondary carbon, but 2 secondary hydrogen. So when you say 1 secondary, I hope that you mean by 1 secondary carbon, but it means that since the CH2, it gives you 2 secondary hydrogen. So going back, we have 6 primary hydrogen responsible for 40% of the product. Yes, on the product side, yes. So 6 primary hydrogens responsible for 40%. This is coming from 6 hydrogens. And the major product is coming from only 2 hydrogen. What does that mean? It means that is not the ratio of reactivity or faster reaction for secondary compared to primary is not 4 to 6. It has a higher value. It's even more significant, because 60% of this product is coming from only 2 hydrogen, and 40% is coming from, so you see we have 2 hydrogens here. Any of these can be replaced and it gives you 60% of the product. And 6 hydrogens, these 2 CH3s, can yield to only 40%. So if 40% you divide by 6 hydrogens, 40 divided by 6 hydrogens, and 60% you divided by 2 hydrogens. So basically this gives you 30% of the product per hydrogen. 30% of product is coming from every one secondary hydrogen. And in this case, is a 40 divided by 6. So that's, yes, the percentage will be given to you. The percentage will be given to you, but the main idea is to understand that secondary hydrogen is more reactive, or secondary free radical is more stable than primary. This is the whole idea. I mean, after you finish chapter 4, you're not going to do any of this calculation, but you would always use the fact that a tertiary free radical is a lot more stable than secondary more stable than primary, and primary is going to be more stable than methyl free radical, because that's different from primary. This is a methyl radical. That means there is no carbon attached to this free radical, but if you have one carbon attached, this is a primary. So we have a primary, and this is a methyl. So the idea of tertiary free radical being more stable than secondary, more stable than primary, more stable than methyl should stay with you, and that's why I'm repeating so many times that I want to make sure 95% of the class is going to hear this couple times at least, because some of you would hear for 10 times for everybody to hear 2 times. So to make sure at least 2 times. So that idea is going to stay with you. But calculation only for this chapter, yes, percent will be given. And then you have the structure, then you can find activity or reactivity of secondary carbon or secondary hydrogen compared to the primary. So this is going to be a lot more reactive. Tertiary. This is a tertiary hydrogen. How do we know it's a tertiary hydrogen? Because this carbon is a tertiary carbon. So this hydrogen is going to be tertiary hydrogen. If you change that with chlorine, that means you are chlorinating a tertiary carbon, or you are replacing tertiary hydrogen with the chlorine. So 6 point, that value that I couldn't force my brain to come up with, is 6.7% of the product coming from each primary hydrogen, because you divide 40 by 6, and then 30% of the product is coming from a secondary. That means secondary free radical is more reactive than primary free radical. Does it make sense? You see, you learn the baby steps first. First, you have to learn about activation energy. You have to learn about stability of the product or stability of the intermediate. The more stable the intermediate, the faster the reaction. The faster the reaction would yield major product. So if this is a major product, that means the intermediate that is it's yielding this product is going to be more stable. Activation energy for this one is less because it yields major product. Okay, this diagram here, it shows, this diagram here, it shows the stability of secondary free radical compared to the primary free radical. Secondary free radical has less energy, less internal energy. It means that it's more reactive, more stable compared to primary. Okay, so now that you know about thermodynamic values, what does this trend tells you? The trend in energy for methyl to remove the hydrogen from methane to go to methyl free radical. You need 435 kilojoules of energy. To remove hydrogen from primary, you need 410. From secondary, you need less energy. From tertiary, you need less energy. So what does it mean? It means that this tertiary can form faster because it requires less energy. So basically, the activation energy for formation of tertiary free radical is less. And if the activation energy is less, it's going to be faster, it's going to form faster because this one is more stable. So tertiary is more stable. And what you need to know by heart, and if someone wake you up middle of the night and ask you which one is stable, you should be able to say right away, tertiary free radical is more stable than secondary, more stable than primary, more stable than methyl. So even though the R is representative, it can be hydrogen or carbon, but that's like only when you're dealing with the some functional groups. But in general, the R group meaning that there is a carbon there. So if it's a hydrogen, we write hydrogen. If it's carbon, is going to be represented by R. It doesn't matter if there's a methyl group attached here or is a H3CH2, which is the ethyl group, but still is the carbon that is attached to this carbon. It's a carbon-carbon bond. That makes this carbon to be a tertiary free radical. Any questions? Does it make sense, the delta H value or the enthalpy? The greater it is, that means the activation energy is higher, slower reaction, and the faster the reaction, the more stable the product or the intermediate, reactive intermediate. Any questions? No questions? Okay, tertiary more stable than secondary, more stable than primary, and that is more stable than methyl. A tertiary hydrogen is 5.5 times faster than a primary. Also, that's even more than the secondary compared to the primary. Is a lot more reactive. Comparing bromination with chlorination. So for bromination, you get primary only 3%, but secondary 97%. What does it mean? That bromination is a lot more, the difference between primary and secondary for bromination is more significant. And that translates for bromination being more selective. More selective toward what? More selective toward formation of the product. More selective when you have the choice of going for primary or going for secondary. When you have more selective, it's going to select more stable intermediate or reactive intermediate. So bromination is more selective and is going to give you 97% of the product as the secondary bromination and only 3% for primary bromination. If you look at the energy diagram for bromination, for the bromination here, you would see that highly endothermic. So you can conclude any reaction that is endothermic because it's going to demand energy from outside. It can also be more selective. is less reactive but more selective. Chlorination is exothermic reaction, and it is less selective because chlorine is more reactive. More reactivity, less selectivity. That, I guess, happens in real life too, right? So if you're not very selective, you could, you could find, you can't be very selective if you're very reactive. If you want to get something like really fast, and if you like to feel, if you want to, if you're really hungry and you want the food, you can't be like very selective that it has to be that specific restaurant for you. But if you are very selective, then that means that you're not that hungry. You can actually wait longer to go to that specific restaurant that is in your mind. Because if you are very hungry, you're not going to do that. You're just going to say anything, any food at this point. It's just going to be is fine. But if the restaurant that is in your mind is like 1 hour away, and you are going to wait for that, you're not going to suffer for one full hour. You would eat something. So if you are more selective, means the reactivity is less. And then the reactivity in that example is just the degree of the hunger, how fast you want to get to that food. So if you're very selective, it means you're not very reactive. In a face-to-face class, I use different example. I was using like a teenager or someone like older, but since this is recorded, food, it just came to my mind and is a perfect example, and it works. I don't know if you had breakfast or not, but it does work. Okay, because it's not good to talk about food when people are hungry. Chlorination versus bromination, energy diagram, and Hammond postulate. Hammond postulate, what is Hammond postulate? It says that for something or reactant that is not very selective or if it's very reactive, transition state is closer to the reactant, and when it's closer to reactant is in energy and in structure, because the energy diagram basically shows how does the structure look like, because the energy diagram is calculated based on structure of the reactant going to the product, the time that is bond breaking, the new bond forming, and the energy of the molecule is changing, and they monitor that energy and they put in a diagram. So for chlorination, which is the exothermic reaction, we see this transition state is very close to the reactant, and for bromination, the transition state is very close to the product. So I don't know if the example of the food is going to help here, but example of the other reactivity based on the age of someone looking for a better half is like if you are not very selective and then you get engaged at very young age or very early in the stage of knowing the other person. If you are very reactive and you just jump into engagement, you are still being yourself and your half is being, themselves. You haven't been, compromised. You haven't done anything to get to know each other and be very close to like what a married couple would look like. But if you are very selective, you're not going to jump into the transition state early. You're going to wait if the transition state is like engagement. So you're not going to jump into transition state very early. You're going to take your time because you are very selective. And by the time you get to the engagement, you're almost acting like a married couple and you know each other like much better. So if it's selective, the transition state is going to be very close to the product. And if it's reactive, transition state is going to be very close to the reactant. So product for product-like, that's for endothermic reaction. Reactant-like, that is for exothermic reactions. And that is known as the Hammond postulate. Endothermic reaction is going to be product-like for transition, and for exothermic is going to be reactant-like for exothermic. Okay. Can you take a screenshot of this diagram for me? And yes, I will ask you to send it later. Just take a screenshot of it, please. It's a very important slide. Thank you. Okay, the diagrams, we have endothermic. This is the endo. The two out. Oh, I make the folder. I make the folder. Endo for endothermic reaction. This is the exothermic reaction. What is happening in the transition state for exothermic reaction? For exothermic reaction, transition state, it looks like still like a reactant. You see, hydrogen is very close to chlorine. This molecule, to me, it looks like more of a methane than chloromethane. But for selective reaction, that you have your transition state close to the product, the hydrogen is almost detached. It's almost detached, so this one looks like the product already. It looks like that you have removed the hydrogen is removed, and you have a free radical forming, because the distance between the carbon and hydrogen, it shows like how engaged is hydrogen with the carbon. So for exothermic reaction, it's very close to the reactant. For endothermic, it's close to the product. The idea of activation energy for endothermic reaction is a higher activation energy compared to this exothermic reaction, or for exothermic reaction, the energy of the reactant and product is much lower energy compared to the reactant. And for the endothermic, it's like basically summary of a lot of that we have learned today. Radical inhibitors, those are inhibitors that said like something like vitamin E or vitamin C, that they are hope to be inhibitors for aging, is going to cause obstacles for the free radicals that they cause aging. It is going to provide the free radical for them to stop. So free radical chain reaction is fast and has many exothermic steps. So it's going to give you like more free radical. The free radicals that are forming, they're very free radicals are reactive, because that's why they're called the reactive intermediates. Beside free radical, the other intermediates that you are going to face and study for next chapters is carbocation. What is carbocation? Is a carbon that has lost electron. So basically the cleavage is heterolytic cleavage, not hemolytic cleavage. So let's say if you have a carbon-chlorine bond and you spend energy to break it, it's going to most likely break easier if you do a heterolytic cleavage. Take the chlorine, make the chlorine leave with 2 electrons, and then carbon is going to carry plus charge. Then you end up with carbocation. Carbocation is the carbon that it's electron deficient, is missing 2 electrons from its octet satisfaction. Is going to be very reactive because carbon is not stable when it's electron deficient. With only 3 bonds, it's not very stable. But the idea of carbocation if it's being tertiary, secondary, or primary. Which one is going to be more stable? Just like free radical, because free radical also is an electron deficient. Tertiary is going to be a lot more stable because alkyl groups that are around positively charged carbon, they are, by experience has shown that they are electron donor. They're going to support this plus charge. They are going to be stabilizing the plus charge. So the more of those R groups that you have, that they can support the plus charge, the better off that charge is going to be, and more stable the plus charge on the carbon is going to be. So for methyl free radical, for methyl free radical, there is no supporting R group. For the primary, you have one R group, and for secondary, you have two R groups supporting. For tertiary, you have two R groups. That's like in rough time, if you have siblings that they are generous. I mean, they must have sibling and they must be generous. So if you have one generous sibling, you have two generous siblings, and you have three of them siblings that they are generous, you probably are better off when you are surrounded by more generous people in rough times. Now, it's not just people that they are also generous. How alkyl group are supporting the plus charge? They can affect by inductively, so it's like an inductive effect. So it's just donating electron density with the sigma bond. That's inductive effect. So electrons are not transferred, they're just spending more time around that plus charge, so it's supporting. And hyperconjugation, that's like the electrons overlap of the sigma bonds with the empty orbital. When you have carbocation, what is the hybridization of carbon in carbocation? sp, sp2, or sp3? Hybridization for carbocation. sp2, very good. And do you remember when we talked about sp2, we had one p orbital that was empty. It was a unhybrid p orbital, and then we had sp2, sp2, and sp2. So if we have carbocation, that means we have empty p orbital. So when we say hyperconjugation, it's like overlap of the sigma bond or electron from the sigma bond with this empty orbital of the unhybrid p orbital. And this happens when you have the hybridization as sp2. Hybridization for free radical is also sp2 because electron domain counts as sigma bond and it counts as pair of unshared electron. It does not count as single electron. The single electron still is like empty orbital. So that's not, it doesn't count as the electron domain. So when you are counting number of electron domain, to find hybridization for free radical is sp2, for carbocation is sp2 also. So tertiary more reactive than secondary, and secondary more reactive than primary, primary more reactive than methyl carbocation. Stability of free radical, the same. Tertiary greater than primary, secondary greater than primary, greater than methyl. For carboanion is the opposite. For carboanion, methyl is going to be more stable, and then it's going to be primary, it's going to be secondary, then it's going to be tertiary. This is for carbanion. Why carbanion? This one is more, methyl carbanion is more stable than primary, because carbanion is a carbon that carries a negative charge. When carbon carries a negative charge, when it's primary, is less hindered. It already has too much electron density around it, so it doesn't need extra force or steric hindrance from other groups. So primary is going to be for carbanion more stable than secondary than the tertiary, because it doesn't like too many groups around it. If you have carbocation, we classify that as an electrophilic. Free radical is also electron deficient, so it's looking for electron. Carbocation is electrophile, is looking for electron. Carbanion, it has extra electron, and because it has an extra electron, is looking for positives to share that later, or to share that via bond, with empty orbital, with a Lewis acid, with something that is looking for electron. So it's looking for positive charge. That's why it's called nucleophile. So nucleophilic, meaning something that is looking for nucleus. What do you find in the nucleus? Is a plus charge. So it must have a negative charge already, or it must have pair of unshared electron already, that is able to donate or share with something that has positive charge, or it has empty orbital. Electrophilic, meaning that it's looking for electrons. That means it must be positively charged or partially positive charge. So if it's partially positive charge or partially or complete positive charge, is acting as electrophile, is looking for electrophile. Now, what about carbene? Carbene is a special case. It has only 3 electron domains, so hybridization for carbene is also hybridization for carbene is also sp2, and if it's sp2, it means that you're dealing with empty orbital. So it has empty orbital and it has pair of unshared electron. It can act as both nucleophile or electrophile. Questions? Any questions you might have from chapter 4? So chapter 4 is a study of chemical reactions for alkane. Specific reactions that we emphasized on is halogenation. Halogenation, and then with the halogenation, fluorine was too fast, iodine was too slow, and we concentrate on chlorination as an exothermic reaction, comparing to bromination for endothermic reaction. So those are just examples that's showing for exothermic reaction how does energy diagram look like. The transition state is close to reactant. For endothermic reaction, the energy diagram product have higher energy than the reactant because it's endothermic reaction, and transition state is close to the product. Endothermic reactions of bromination is more selective because transition state is product-like, and for exothermic is more reactive, and transition state is very close in structure to the reactants. Chapter 3, you have question, Jordan, for the chapter 3? Or assignment, and we're gonna work as a group with the class to come up with the answer to those questions that you have. So if I say something that doesn't make sense, well, yesterday, believe me, after running upstairs 2 times before I was able to even um, connect. And coming down, it wasn't a good situation. The class was right after I was writing the quiz. I was so concentrated on like the parentheses that I did not cover for you in previous lecture. And I was so worried about you, and I was trying to emphasize if there is a parenthesis with 3 CH3s, make sure to open that I even missed that priority for OH bond. And the OH bond I counted as a hydroxy group instead of naming that compound as alcohol. So if I make a mistake like that, sometimes it's accidental, sometimes it's intentional. Please let me know. But yesterday, not intention. It was just a pure mistake that I made. So the groups, like let's say if you have a C, H, and then CH3. So you have a CH2 here, and this is 1. Then you go to CH2. Basically, 5 bonds. If you think that the CH3 is within the line, that means you have 3 hydrogen attached to this carbon and 2 carbon attached to this carbon. So that makes it 5 bonds. That's not possible. So if it's written in the parenthesis, that means it's attached to this carbon, not the 2 other carbon on the site. It's not this and this carbon. It's just this carbon. So parenthesis something. So if this is like a C, only not CH, and it's 2, that means you have CH3 up and CH3 down, so you can open the chain. Now, your question, before you forget your question, which question of chapter 3 OR app? Jordan. Well, since it's assignment for grade, I will answer a few of them. I will help you with few, and then you can answer and show me your answer. 7 to 10, that is 7 to 10. Oh, that's just naming? Nomenclature? Yes? Okay. Nomenclature. I think for the exam, since we have not read about, we haven't really talked about naming of alcohols. For your exam, I'm not going to use the alcohol or aldehyde or other functional group. Maybe just the halogens and then the alkane. For the functional group, yes. For the functional group, I'm going to ask you, but I'm not going to ask you about the naming other functional group. So let's look at the question 7. Since you said 7, we already talked about question 10, that you have to open the parentheses and then you have the longest carbon chain. Due date for the co-op and for OR. The dates that I think I mentioned that like a couple of times, and I'm glad you asked that question now. The OR app assignments and co-op assignments, they are due before your exam. The suggested due dates that I have for your in your syllabus. Then you have the those are suggested. So now the last due date or the absolute due date is the time of the exam for any co-op and for any OR app assignment. So if you turn those in May 26th, you're fine. The syllabus, even though I had to change it because I had similar question to change the date, but is going to be due the day of the exam. Alex, how did you name question number 7? Sorry, Alexa. For question number 7. I mean, if it's hard with the line angle, if it's hard for the line angle, then you can just write the change to the condensed structure. Write the molecule in a way that you can see better, because this is like first chapter with the naming and is training for you. So you have believe me, it's going to be much easier if you write the condensed formula instead of the line angle to begin with, because you do have time. So then you could see all your carbons, and you can draw the structure in a way you can name it easier. So we have a CH2, we have a CH and a OH attached and a bromine attached. I'm looking for the question number 7. So you have to look for the longest carbon chain. So if you were looking for the longest carbon chain with the OH in that carbon, we cannot just go with the longest carbon chain and not include the OH. So we have to make sure that OH is part of the major carbon, okay? Major carbon chain. So you have to start closer to the major functional group, which is the alcohol. So it's based on the IUPAC. So you have to take your carbon number 1 for the carbon that is attached to the OH group. And this does not make sense with everything that we talked for alkane. That's why I said for the exam, I tried not to include the OH, so you don't get confused with that. And then you are going to move up to this carbon that is next to, okay? Then you look for the longest carbon chain that gives you greater number of branches. If you go to the right side, you get 3 and 4. You get 3 and 4, and with that you would get 1, 2, and 3 branches, 4 branch here, and then the bromine. But when you go to carbon number 2 here, if you go straight up, you are going to get T-butyl as the major branch, 1 branch rather than the 2 branch. So when you start with the OH, carbon that is attached to OH is something we have not talked about yet, but since you asked me and is in the app, I'm going to explain that. You start with the carbon that has the OH. Then that carbon is going to be 1. You have to go up next carbon to make it 2. Then you have a choice going straight up. So you have to start here. You can go to the ethyl group, or you can go to this propyl group. So you have to T-butyl group side. You want to make it longest carbon chain, and if I make any number here, 1 on the line angle, and I show you. So this is your carbon 1. 1, 2, 3, 4, 3, 4, 5. So it would be 1, 2, 3, 4, 5, 3, 4. Okay. Can you see this? Oops. I started with 8. So now, can you see that 8? This was 8, sorry, I missed the... See the 8? Okay. So that was for the OH, because now today I have to worry about the OH now. So you have to start numbering for carbon that is attached to OH or close to the OH, and then you go up 2, 3, 4, 5. Now, the higher number of carbon in the main carbon chain, it takes priority over the number of the branches, because if you go down here, you get to 3 and 4. If you go up, you go to 5. And it's better to number it. Sometimes you number it with like different colors and compare it. Now you have T-butyl group. This is a T-butyl group for attached to carbon number 2. You have a methyl group attached to carbon number 3. And you have a bromo group attached to carbon number 1. So if you draw it for yourself and then we just follow it, numbering. So carbon attached to OH is going to be carbon number 1. Then 2, then you go at the top branch that you have the ethyl in order to get 5 carbons there. Then you circle the branches, name the branches. So you have T-butyl, methyl, and you have a bromo. So if you have a T-butyl, which one should come first? Butyl or bromo? Then alphabetic order. So you just go instead of what? Why is the T-butyl bromo? We have a BR, that would be bromo. B-R-O-M-O, bromo. Okay. So T-butyl, it looks like this. A carbon that is attached to 3 methyl group now is attached to the main carbon chain. So if you take this cross sign that you have for your structure for molecule 7, that looks like the T-butyl. That's the 1 carbon attached to 3 methyl group. So that would be your T-butyl. Okay, and then you have the methyl group attached to carbon number 3, and you have a bromo, that is the Br. In organic, you don't say bromide unless it's ionic compound. So for ionic compound, it's bromide, but in this case, it's going to be bromo. So it's a 5 carbon alcohol with 3 branches on it. So it's going to be butyl, bromo, and methyl. Put them in alphabetic order. What would be the alphabetic order? It's going to be 1 bromo, right? Bromo. It's not a bromyl. It's bromo. B-R-O-M-O. Bromo. Very good. Yes. 1 bromo. And then it's going to be 2 butyl. Okay. 1 bromo, 2 T-butyl, because it's a T-butyl. And then it's going to be 3 methyl and 5 carbon alcohol. 5 carbon alcohol. There are 2 ways to name it. It's going to be pentane, 1-ol, or 1-pentanol. Okay, pentane, 1-ol, or 1-pentanol, because you have to give the location if the OH is attached to carbon 1 or carbon, whatever carbon, 2 or 3. So you have to give location to the OH also. But the choice is going to be 1-pentanol. The other choice, I'm going to write it and then you can take a screenshot if needed. 1 bromo, 2 T-butyl, 3 methyl, pentane, 1-ol. This pentane 1-ol or 1-pentanol, it's not that long ago, 1997, they said both of these are acceptable and they are still accepted by the IUPAC. So if you see 1-pentanol versus pentane 1-ol, both of them is correct. This is the only case that is the new and old as of 1997, okay, which I was actually teaching then. So it's not like a, it's not that old of a rule. As of 1997, they said like for whatever rhymes better for you. For me, it's like a 1-pentanol. Then if it's easier for pentane 1-ol, both of them are IUPAC recommendation, and you can use either. So I have two names with the blue color there for that compound number 7. If you want to look at it, take a screenshot, or I read it for you to write it down. And if there is any problem, tell me now. So if I made a mistake, I correct it. You got it? Okay. Sec-butyl. What is sec-butyl? Sec-butyl is, let me see if we have a sec-butyl here attached. We don't have any sec-butyl on the example of 8, 9, and 10, but we do have T-butyl. We do have T-butyl, but we don't have sec-butyl. So I'm going to show you how sec-butyl is going to look like. So if you have this structure, T does not count for T-butyl. That's right. The only prefix that counts is iso. If you have this group attached, is 1, 2, 3, 4 carbon, but is attached from secondary carbon. This is called sec-butyl. So this branch is called sec-butyl. Okay. Sec-butyl is like you have a 4-carbon branch, but is attached from second carbon rather than the first carbon. So that is a sec-butyl. And then butyl is going to look like this. I'm going to show you one more time, even we have it somewhere else also. 1, 2, 3, 4. Okay, this is a butyl attached. Butyl, you have 4 carbon attached, because if I go straight, I have 1, 2, 3, 4, 5 carbon on either side. So I take this as a branch, but it's 4 carbon attached from the first carbon. So this is the first carbon. I see that I'm going to show you the carbons. So first carbon is attached to the main carbon chain. So this is butyl. But in this case, when you have a carbon chain that is 4 carbon as a branch, your branch is longer than methyl and ethyl. So you have a branch, but it's attached from second carbon to the major carbon chain, is going to be sec-butyl. So we have butyl, but this one is a sec-butyl. And for T-butyl, it looks like this T that is attached to the major carbon chain, main carbon chain. And if you look, if you put carbon in every cross and beginning of the line, you would see 4 carbon there also. Okay. This is a 4 carbon, 1, 2, 3, 4 carbon. It looks like a T with respect to each other based on the arrangement. And it's called T-butyl. The group is called T-butyl. So we have T-butyl, butyl, and this is a sec-butyl. Okay. Any other questions? No questions? Isobutyl. I was thinking should include also isobutyl on this page so you are reminded of all butyls, but let me do that. see this branch? How many carbon you have on this branch? If you cannot see isobutyl there, add the carbons. Okay, add the carbons. If you couldn't see it, add the carbon. 1, 2, 3, 4 carbon. I have 4 carbon on this branch. It's attached from the first carbon. So I'm tempted to call this butyl, but it's not butyl because butyl is a straight chain carbon here. Is the straight chain carbon for butyl. This is 4 carbon attached, but it looks like an iso. Why it looks like an iso? Because there is a methyl on the second carbon. So methyl on the second carbon, it makes this butyl like an isobutyl, but is attached from the first carbon. That's the difference between an isobutyl and a sec-butyl. Sec-butyl is attached from second carbon, but isobutyl is attached from first carbon, but there is a methyl group next to it. So if you see like a Y shape attached to the main carbon chain, that's like isopropyl. See this? This looks like a Y shape. That's isopropyl. There is no carbon between this main carbon chain and this isopropyl carbon here. Okay, that's 3 carbon, so it's isopropyl. Isopropyl. But when it's a isobutyl, it looks like the it looks like a Y shape, but it has extra carbon attached to it, so it's like a Y with the tail. And propyl would be the straight 3 carbon. Yes, propyl is when you have the 3 carbon attached. It doesn't have to be like straight, but yes, 3 carbon is 3 carbon attached from the first. That would be propyl. So this is the example of propyl. In number 8, does the Cl takes priority? No. OH always takes the priority. Cl does not take the priority. Let me go to 8. OH takes the priority. So you have to number from the side that is closer to the OH. If I go from 1, 2, 3, 4, so I have to number from this end. 1, 2, see this one is the 1, 2, 3. That because this end is the closest to the OH. So OH takes the priority. 1, 2, 3, 4. If I go up here, it's going to be 5 and 6. If I go down here, I get more carbon. So I'm going to be 1, 2, 3, 4, 5, 6, 7, 8. So this is basically octane. And then you have this Y shape. So this Y shape is not scientific name, but I just say it because it makes it easier for students to recognize for the line angle. So you see this Y shape attached major carbon chain is going to be isopropyl. And then you have isopropyl here. It was 8 carbon. OH is on carbon number 3. Isopropyl is on carbon number 4. And then chloro is on carbon number 6. Was it 6? 3, 4, 5, 6, 7, and 8. So you have 6 chloro, 4 isopropyl, 3 octanol, right? 6 chloro, 4 isopropyl, octanol. Is that right? Chloro, 4 isopropyl, octanol. I'm going to give. I have to give the location. 3 octanol. You have to give the location also. 3-octanol. Yes, 3-octanol. Very good. Any other questions? I still need that screenshot. I should have done like 2 or 3 because I do that in the for the lab, but I asked just once. So. 9. Okay. Let me look at 9. Counting the longest carbon chain. You have to find 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. So you have only one way to go. One, and then when you have only one longest carbon option, so you are going to draw a line that you know you are going that way. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so it's going to be 9 carbon there. Now the question is, should you number it from this end or this end? You have to name both of them and see which one would take the priority. So if you go from this way, you're going to get a 2, 3, 4, 5, 6, 6. If you go from this side, you're going to get 1, 2. You're going to get 3, 3, 4, 6, 7, 8. You add those numbers to see which one is going to give you better. It has T-butyl on carbon number 4. Okay. Ethyl group on carbon number 1, 2, 3, 4. You're counting from left. Maybe that is correct, maybe not, but you have to look at both options. As I said, you have to put those numbers together and see which one would come up with the lower number set. Okay, I don't want to give you the answer because I'm grading this, but I'm telling you, you can write it quickly. If you go from top, which is the left side, if you go from top, you're going to end up with 2, 3, 4, 6, right? 1, 2, 3, 4, 5, 6, 7, 7. If you go from this end, you're going to end up with 3, 3, 4, 6, 7, and 8 to have. You got it? And then you just put the branch, name for branch, give location for each branch, and put the molecule together. And when you number, you actually write the numbers down, because you might count like 8, and then when you write it, it's like, no, it was 9. Why did I count 8? And it could happen to anybody. So I think if you come from this side, from the left side, you end up with like a 7, 7 here. That's going to give you a high number. Versus going from this end, that would give you like a 3, 3. So, but it's better to write both sets and add them up. Whichever is lower, that would be correct. But there's only one choice of the carbon chain. This is the only carbon chain you have there. For it. F, that's on which page? F. What's the topic? What's the page? Stability of alkane. F. Stability of cycloalkane. That's the whole chapter, and your quiz is all about stability of cycloalkane. You get more than so. Is that only for cyclohexane you don't get it yet, or is the propane, butane, pentane, and all of that? If it's only cyclohexane, you are dealing with the interactions of the, it's called the 1,3 interactions. We put this in chair conformation. I just don't understand the chair and how onto the chair structure. Okay. This, if you wrote down everything I said yesterday, because I was trying to go like baby steps. So if you wrote down everything I said yesterday, is going to help you a lot. I'm going to repeat the summary again. We have 3 axials up, 3 axials down. We have 6 equatorials that they alternate up and down. For carbon 1, if it's up, for carbon is down, up, down, up, down. So we have 6 equatorial and we have 6 axial positions for chair conformation of cyclohexane. Now, do you see these 3 white colors that they are too close to one another? Because they are too close to one another, that is going to give the molecule a little bit of a pressure, and just hydrogen is okay, no problem. If I take this hydrogen and put a methyl group or any other alkyl group, is going to have interaction with the other 2 hydrogen. This is a 1,3 interaction or 1,5 interaction, and is not going to make the molecule stable. The molecule is trying to avoid having anything on the axial position unless it's forced to have it. Okay, so if I have one branch, that one branch on axial versus equatorial, which one is going to be more desired? It's going to be on equatorial. So you have to write these down for yourself, the scenarios. You say equatorial is preferred position for any branch to begin with. So if you have only one, you place it in equatorial. You have 2, then depends on the position that they are asking to put. Is it going to be cis or is it going to be trans? If you have 2, if both of them goes to equatorial, is better. If one goes to equatorial, one axial by 4. Okay, if both of them goes to axial, is a disaster. So it depends on the name they are asking. So you have to pay attention to the name of the cyclohexane. If name of cyclohexane is 1,2 trans, do you have the models or you don't have the models to build it yourself? Okay, if it's a 1,2 position, okay, if it's a 1,2 position, and then if you don't have the models, then you have to basically draw that structure that I showed you for cyclohexane and label equatorial, label axial, and keep in mind equatorial is preferred. And up and down, you have to draw the axial, equatorial, up and down. Alternate axial up, axial down, axial up, axial down, and then for every carbon you have one equatorial that is opposite position to the axial. So if the axial is up, equatorial is down. And for second carbon, equatorial would be up, axial would be down. So you have to feel these positions first. So if the equatorial for the first carbon is down, equatorial for second carbon is up. So if you have a 1,2 trans, both of them can go to equatorial because the first equatorial is down, second equatorial is up. So you have opposite side, one is down, one is up, and it rhymes with it goes with the trans and perfect, and both of them equatorial, then it's good. But if is cis 1,2, you put the first one in equatorial, okay, the first one in equatorial, but if it says cis, the other position that cis is not a choice. Out of your choice is going to be axial. So you have to put on one equatorial and one on axial. You have no choice. You have to put that one equatorial, one axial. Then, okay. If it's a 1,3, then you have to look, is it cis or is it trans? If it's cis, you can put both of them on equatorial, because if for one equatorial is up, what happens for two? Equatorial would be down. For 3, equatorial would be up. So if you have a 1,3 cis, both equatorials would be up. And since both of them are up, it's going to be both on equatorial and a cis, and it's going to be stable. But if it's a 1,3 trans, then you don't have much of a choice. Then it's going to be, if the first one is equatorial, since the position 3 equatorial is up, axial is down, and you want to make it opposite, so the other one has to go to axial. Okay. I hope that helped, but the best thing for you to draw, since you don't have the models yet, it's best for you to draw. There are cheaper versions of those models that if you can order it, they don't look like the balls and sticks like this, but it's just the more of the sticks, basically. That still is going to help you with the building molecules, if you find or used one. For chapter 5. For chapter 3, it might be too late, but for chapter 5. Okay. Will there be a quiz for chapter 4? Yes. I'm going to have to put that for Sunday or Monday. Which day is better? I guess Monday is holiday. I'm going to put it on Sunday. Yes. Sure. I agree. Questions? Any other questions you might have? Did anybody start the quiz? Let's see. Okay, quiz is up. I ordered a pen for my Surface, and it's not here yet, because what I have, it doesn't write very clear. Let me know if you have any other questions. Just want to make sure. Okay. Make sure you're not taking the quiz. Okay. Let me see if there was a question here. Not yet. Sunday. Where do we submit the screenshot? I have to generate. I have to make the folder for you. No, the exam is not going to be class time because I'm not moving with the schedule. I actually benefit from that class time. For the chapter 5. because I didn't start my chapter 5 today. It was on my schedule to start, so I would use that exam day for to cover chapter 5.